Swayam Prabha. Digital India. Educated India.
In the previous lecture, we discussed in detail op-amp circuits. We looked at a couple of example op-amp circuits, and also I emphasized that op-amp has to be used in negative feedback, and I also mentioned how to find the signs of the op-amp in any circuit such that it is in negative feedback. Okay, an op-amp is basically a voltage controlled voltage source with a very large gain. Because the gain is very large and it's in negative feedback, it forces the input signal of the op-amp to be a very small value, which can be considered to be 0. And if the gain of the op-amp goes to infinity, that is the idealized version of this, which we call the ideal op-amp. In that case, the input difference voltage of the op-amp can be is assumed to be 0. Okay, and there is no input current into the op-amp. So based on these things, you can analyze any op-amp circuit that you have. Okay, so if there are any questions regarding what we did in the last lecture, please go ahead now. Otherwise, we'll start with today's topics. So far, we have looked at circuits that have resistors and control sources and so on, and all these are known as memoryless elements. What is meant by this is that the current at instant t depends only on voltage at instant t. That is, it doesn't depend on the voltage at any other instant. Okay, or similarly, if you have a voltage to current relationship, the relationship is exactly the same and for all instants, and more importantly, the voltage at some instant is related to current at that instant only. Okay, similarly for control sources, the control quantity is related to the controlling quantity instantaneously, only at that instant. Now if we have capacitors and inductors, we know this these properties are not true. If you have a capacitor, the voltage across the capacitor depends on not only the current at that instant, but on the history of the current. Similarly, if you have the current through the inductor, it depends not only on the voltage across the inductor, but on the history of the voltage across the inductor. Okay, so capacitors and inductors are elements with memory. Okay, so what we will do in this lecture is to try and analyze circuits which have inductors and capacitors in addition to resistors. Is this okay? Any questions? So let me take a circuit that we are all familiar with, a resistive divider. Okay, now let's say I call this Vs and the voltage is 0. Okay, what will be the output voltage? Please try to answer this. What is the output voltage? When I say output, in this case I have defined the output to be this particular voltage. Okay, what is that voltage going to be? What will be the voltage here when the input voltage Vs is 0? Anybody? What's the voltage going to be? So this voltage clearly from the voltage divider formula is Vs times R2 by R1 plus R2. Okay, and if Vs is 0, this voltage is also 0. Okay, this is a simple resistive divider. Now let's say it jumps from 0 to some voltage Vp. Okay, what happens then? The output voltage jumps from 0 to Vp times R2 by R1 plus R2. Okay, so you can see that the variation of the output voltage with time, the horizontal axis here is time, this is time, and here also it is time. The variation of the output voltage with time is exactly the same as the variation of the input voltage with time with a scaling factor. Okay, now let's say we do something. We have Vs and I replace R2 with a capacitor and I have R and C. Okay, what happens in this case? Let's say initially the capacitor voltage is at 0. Okay, and the input is also 0. Clearly in that case what happens is that the capacitor voltage is 0, and because Vs is 0, no current flows through the resistor, which means no current through the capacitor. So if there is no current through the capacitor, its voltage cannot change. Okay, so in this case the voltage remains at 0 if the input is 0. Now let's say the input jumps from 0 to Vp. Okay, what happens to the voltage? Please try to answer this. Let me call this Vc. Vc when Vs jumps from 0 to Vp. Okay. Please, some of you attempt to answer this. What is the voltage Vc going to be when Vs jumps from 0 to Vp? Okay, we have an answer. It says that one over C integral I of t dt. Okay, this is correct, but the only issue we have now is that we don't even know what this I of t is. Okay, so that also we have to solve for. I mean, we have done this for the simpler circuit before. The current in this is Vs by R1 plus R2. Okay, whereas here we have to find out, and the current itself depends on the voltage of the capacitor. Okay, so now what I would like to do is to write the equation for this circuit so that I can solve it. What I'll do is this. I'll write KCL at this node. Okay, so the current through this, I will express everything in terms of the capacitor voltage Vc. So the current through this is C times dVc by dt. We know that is the current through a capacitor which has a voltage Vc across it. Okay. Now that has to be equal to the current coming from the resistor. So what is the current through the resistor in terms of Vc? Please try to answer this. Okay, that is correct. So the capacitor current, which is C times dVc by dt, equals the current in the resistor, which is Vs minus Vc divided by R. Okay. What I will do is I will group all of the terms containing Vc to the left hand side, and I will also multiply both sides with R. So I will get Rc dVc by dt plus Vc equals Vs. Okay. Now this is a feature of circuits containing capacitors or inductors or both, that the equation governing the circuit will be a differential equation. Okay. Whereas previously we could write, if I still call this Vc, there is no capacitor here, I will just call that voltage Vc. Vc equals Vs R2 by R1 plus R2. Okay. So it's an algebraic equation. Whereas in this case it's a differential equation if you have resistors or capacitors. Okay. So we have to solve the differential equation to find the solution. Okay. So let's try and do that. So before that we will try and solve a couple of cases intuitively, and then go on to finding the solution of the differential equation. Okay. Any questions so far? So let me rewrite the circuit and the equation again. Okay, this is the circuit, and for arbitrary inputs it's not very easy to solve for these things, so we will take specific kinds of input. So initially, in particular, I will take an input that goes from 0 to Vp at a particular time instant. Okay, so this is t, and let's say this is t equals 0. Okay. And we also know that the differential equation governing this is Rc dVc by dt plus Vc equals Vs. Okay. So now first let's forget the differential equation and try to sketch the output based on what we know about resistor, capacitor and the voltage. Okay. I already said that initially the voltage across the capacitor is 0. Okay. So if I try to plot Vc versus time, okay, before t equal to 0, the voltage will be 0. So that's what I have assumed. Okay. So this is because I say initial condition, but I really mean for t less than 0. Okay, on the capacitor. Now, at the instant that the Vs steps from 0 to Vp, okay, what happens to the capacitor? Will it change? Will the capacitor voltage change? When I say t at t equal to 0, I mean at this instant will it suddenly change? That's the question. What do you think? Yeah, so as Aarti answered, the capacitor voltage cannot change suddenly. Now, as I emphasized before, this means that we are already assuming that the currents are finite. Okay, so if the current is infinite, the capacitor voltage can change suddenly, but the current is finite, and in this case we cannot have infinite current. Okay, because if we do have infinite current through the capacitor, it means that we also have infinite current through the resistor, which in turn means an infinite voltage across the resistor. Okay, so this capacitor voltage will not change, will not jump at t equal to 0. Okay, now my question is, what is the current through the capacitor at t equal to 0? What is the capacitor current at t equal to 0? So clearly it is Vs by R or Vp by R, because the value of Vs is Vp. So the capacitor current at t equal to 0, this is Vp divided by R. Okay, so that means that this current IC at t equal to 0 is Vp by R. Now, because the current is flowing through the capacitor, its voltage tends to increase, its voltage tends to change, and from the direction of the current we know that Vc is going to increase. Okay, so what happens is it increases. So I will show a little bit of increase like this. Now, what is the slope of this increase going to be? What will be the slope? Please try to find out, because we know the current through the capacitor, so we should know the slope of the voltage across the capacitor. Okay, because the capacitor current is nothing but C times dV by dt, dVc by dt. So the current through the capacitor is basically related to the slope of the voltage across the capacitor. Okay, so what is the slope of the capacitor voltage versus time? So when I say the slope of the capacitor voltage versus time, obviously it should have dimensions of volts over time, volts per second, something like that, right? So we know the capacitor current Vp by R. Okay, so we have to equate that, we have to use that in the equation for the capacitor current and find out the slope of the capacitor voltage. Please try to calculate that. So someone please try to answer this question. So the current through the capacitor is Vp by R, which also in terms of the capacitor voltage is C times dVc by dt. Okay, so what I was looking for was dVc by dt, the slope of the capacitor voltage. Okay, so clearly that is equal to Vp by Rc. Okay, so the slope at t equal to 0 will be Vp by Rc. Okay, so it increases a little bit. I have shown it with this blue line over here. Now let's say after it increases a little bit, let's say I come to this point, what happens then to the current through the capacitor? Please try to answer this. Now initially at this point the current equals Vp by R. What will it be at the other point? A little bit, for t a little bit more than 0. The capacitor voltage increases. So what happens to the current through the capacitor in this circuit? Somebody please attempt this. Current through the capacitor here. what happens to the current through the capacitor? So there is an answer that says slope less than 1, but keep in mind that here we are plotting voltage versus time. So the slope is measured in volts per second. Okay. So when we have a dimension quantity like that, it doesn't make sense to say it is less than 1. Okay. So it has to be less than some quantity. Okay. So another answer is that it is Vp by R. But is it true? Why is it Vp by R? What is the voltage across the resistor now? The voltage across the resistor at this time instant. What is it going to be? Is it Vp? Is it less than Vp? Is it more than Vp? Exactly. So the current through the capacitor is Vp minus Vc by R. Now, when the capacitor voltage was 0, the current was Vp by R. But when the capacitor voltage increases a little bit, the current will decrease. Okay. So the current here is smaller than the current there. Now, what does that mean? Because the current is proportional to the slope of the capacitor voltage, or the other way around, the capacitor voltage, the slope of the capacitor voltage is proportional to the current through it. So the capacitor voltage will increase a little, okay, but after that the slope will reduce because the current has reduced. Now if you look at this point, the voltage across the capacitor has increased further. Okay, so that means the current through it is reduced further. If the capacitor voltage increases, the voltage across the resistor decreases, because the capacitor voltage plus resistor voltage equals Vp. Okay, in this time, in this range of time, it equals Vp, which is a constant. So as capacitor voltage increases, the resistor voltage decreases. So the slope reduces further. Okay, so the slope will go on reducing. Okay. Now in reality, it doesn't reduce in discrete steps like this. Continuously it will go on reducing, because as soon as the capacitor voltage increases a little bit, the slope will reduce, then it increases a little further, it will reduce, and so on. Okay. It turns out that the slope will go on reducing, then finally it will asymptotically reach some value. Okay. It will reach some value, and after that the voltage does not change much. Okay. So the slope becomes almost 0. Now what is this voltage? What is the voltage it almost reaches? What is the voltage at which it stops changing further? Please try to answer this. Clearly, if the capacitor voltage is Vp, the voltage here is also Vp, and the resistance has 0 volts across it. So that means there is no current flowing through it. Okay. So the capacitor voltage is Vp and there is no current through the capacitor. So that means that the capacitor voltage will not change at all. Okay. So this would be equal to Vp. Okay. So I hope this intuitive description of how an RC circuit responds to a step is clear. If not, please ask your questions and I will clarify it further. What happens is, let's say you start from a discharged capacitor, that is a capacitor which has no charge, and in this circuit at t equal to 0 there will be no infinite currents, so the capacitor voltage will not change instantaneously, but at t equal to 0, because the input voltage increased to Vp, the current will increase. Okay, so the current through the capacitor increases, and the current through the capacitor will be non-zero, it will be Vp by R. So that means that the voltage across the capacitor increases. As the voltage across the capacitor increases, the voltage across the resistor reduces, and that reduces the current and the slope of the capacitor voltage. Okay, and this happens continuously. The capacitor voltage will increase little by little, and the current through it will reduce little by little, reducing the slope of increase. Finally, the slope of the capacitor voltage almost becomes 0, and you can kind of say that the capacitor voltage reaches some value, and that value is Vp. That's because the capacitor voltage will stop changing when the current through this is 0. Okay, and if the current through this is 0, current through the resistor is 0, the voltage drop across the resistor is 0, so that means that here also you have Vp. Okay, so please think about this and ask me any questions you may have. The slope is Vp by R at t equal to 0. Slope gradually reduces as Vc increases, and Vc asymptotically reaches Vp. What is meant by asymptotically is that it gets very close to Vp but doesn't quite get there. It gets there only at t equal to infinity. Okay, so finally when Vc equals Vp, current through the resistor and the capacitor is 0 and Vc doesn't change anymore. Okay, so any questions about this behavior of an RC circuit for a step input? This kind of input which jumps from one value to another value is known as a step input. Now let's go the other way around, just for completing the calculation. Okay, so let's say initially the voltage Vs is at Vp and the capacitor voltage Vc is also at Vp for t less than 0. Okay, so imagine that we take the capacitor and charge it up to Vp. Okay, so previously we charged it almost to Vp, so we charge it up to Vp, and then after some time we bring the input Vs down to 0. Okay, so this is exactly the opposite of what we had earlier. Instead of going from 0 to Vp, we go from Vp to 0. Okay, so now if you look at the differential equation that governs this circuit, it is Rc dVc by dt plus Vc equals Vs, and this is nothing but 0 for t greater than 0. Okay, so we have a differential equation with 0 on the right hand side. That's the differential equation that governs this particular circuit in this condition. Okay.